Welcome to Playing with Junk, and today I am building a digital clock. Well, you may think building a digital clock, why you don't just buy one? There are so many around, but have you ever seen one with this rotary displays here? Well, if you watched my previous video about aircraft instruments, they may be familiar. I explained how they work, and the problem was I only had 5 working of these digit displays, and for a clock I need 6. So what did I do? I just bought another display unit of this type from eBay, cost about $250. And I removed the mechanical displays, and it turned out that this unit here, which is a little bit a different type, actually had an additional display. So one display was here, here, and another one here. The first one only had 2 displays, this one had 3 digit displays. And that gave me in total about 9 additional displays, which I have right here now. So at the moment I have 13 digit displays. I only need 6 for the clock, so that should be enough. And of course I already made a small circuit to see if everything works as I expect. There is a TTL counter, a decimal counter. It counts from 0 to 9, and then we have here under the wires there is a decoder chip. It's a 74, which one is it? It's a 7442. That's quite a practical, handy chip, because no, it's a 45. The 42 has the same function, but the 45 also has drivers for a 80 milliampere load per input, so I can drive this mechanical thing directly. It only draws 50 milliamps at 5 volts. And you can see it's clocking the seconds here. 9. It jumps the minus sign there. That's the 11th character on this display. And that is just not used, so I can jump that. By the way, you can go to any number you want directly. It just flips around. It doesn't have to display numbers in a sequential order, so you can use that to display random numbers however you want. Okay, let's go to the schematics. I'm using Logisim for simulating that digital stuff, and let's see how that works. Okay, so I'm using the program Logisim, which is a free software you can download. It runs on Mac, on PC, on almost everything, and it's quite handy and it's not bad. And yeah, so what's a digital clock anyway? A digital clock is not more than a counter of seconds, minutes and hours. So we start with a counter, and we find counters under storage. I'm sorry, this is the German version of the program. I think there is also an English version, but I didn't find it so fast. Okay, counter. We take that one, and the properties we can see here. It's an 8-bit counter now. I only need a 4-bit counter. And it should count not to F. That would be a binary counter. So that's the difference between a binary counter and a decimal counter. A decimal counter counts from 9 to 0, from 0 to 9, and then resets back to 0. And the binary counter counts to full 4 digits, and that's up to 15. So I type in number 9. That's a bit weird because in the first moment it shows F again, and then when you select it again you see 9. So we have a counter. What we also need is a clock impulse, a clock signal. That's here. I'm placing it here and connecting it to the counter, and I say activate that clock, and I can also say it should be 2 Hertz because that would be the right frequency. So you can already see it's counting up to 9 and resets. And the handy thing is a decimal counter that exists in TTL logic. It's for example a 7490 or a 74390. I will take the 390 because that has 2 counters in one chip. Then we need a decoder to make 10 outputs out of the 4 data bits that I have. So my decoder here only has 1 input. I need one that has 4 inputs. That gives, of course, 16 outputs, 0 to 15. So the output is here, and that's a bit special with this counter thing. They make only 1 line for all 4 bits, so that's a 4-bit bus here, and the decoder also has a 4-bit input bus, so we only have to draw 1 line instead of 4 or 8 lines. How many, doesn't matter how many data lines we have. Then I will take an LED and connect that here. Okay, we need not only 1 LED, we need 10 LEDs. So I copy and paste that, and then I select both, copy, paste, and then I select 4, copy, paste, and we have 8, 9, 10. Why is it not counting? Okay, I see. I connected the input of the counter, now it is working. That's the output Q, of course. Okay, that's our 1 second display. Then I copy paste the entire thing, and that's our 10-second display. Of course it must only count to 5, so 0, 1, 2, 3, 4, 5, and that's already done here. Okay, now the input of that can be taken from the highest bit here, And there is something we have to change. Now it triggers on the rising edge of the signal. We change that to the falling edge because that's also the case in the chip we will take. Okay, now let's see. 8, 7, 8, 9, and it jumps here. Okay, so that's okay. Then we need exactly the same thing. Copy paste. For the minutes, it's exactly the same circuit. I also take the signal from here and go into the next counter here. So we already have seconds and minutes. There is a little problem. We need to reset this counter when the 10 seconds jump to 6, because 60 seconds is something we don't need to display. So I take the 6th output here and route it to the reset pin here. That's reset to 0, and now we can see what's happening. Let's increase the frequency. Okay, oh, that's a bit fast. We can't see what happens. Okay, yes, it goes to 5 and jumps back to 0. So that works. And we need to do the same here. No, not that way. Sometimes it is a bit tricky to draw the lines, but after a while you figure out how it works. Okay. Let's go to a higher frequency. So that one is acting a bit weird here. Well, it seems I found the problem. I just wanted to delete that and take another one, and as so I made a bridge between the input and the reset pin. So that of course is not good, because I don't want to reset it all the time. Okay, now it's working. You see 0, 1, 2, and then 3. Okay. So what do we need? We need also hours. So then copy paste that again. Okay. So that's okay. We need 10 hours, but here we only need 0, 1 and 2. I want a 24-hour clock, so we can delete all that. And we also don't need this reset line. Okay, the input here goes to the highest bit here. Now the hours are a little bit more complicated to reset. Well, complicated is not the right word. So that works by itself. It counts from 0 to 9, then 19. And when this one is 20, we only have to go to 23, and at 24 we have to reset both of them. So I connect the reset inputs together, and we need 24. That means we have the 2-bit and the 4-bit. That's 1, 2, 3, 4. Let's go here. So it means we need 20 and 4, and you may guess it, we need an AND gate. Looking downwards, okay. Now we have an AND gate with 5 inputs. I don't need 5 inputs, I change it to 2 inputs, and we connect that, and that goes to our reset line. Now let's test that. Now we make here 2, here 3, and let's see what happens. It should jump to 0, 0. Yes, it does. Okay. So that's the clock. There is now something missing. The problem is you have to set a clock to the right time. So there, at the moment, there is no buttons, nothing to set this clock correctly. So what I need is 3 or 4 buttons. The first button I want is one that stops the clock here. I could use a switch, an on and off switch, but I decide to use a push button. I move that here. So, and we need an AND gate. Where is it? Here. Facing up. Deleting that. The AND gate should have 2 inputs. And what's happening is now this. We connect the input here. And I connect my button here. So, as long as the button is 0, the clock impulse here gets blocked. It doesn't pass the AND gate. Only when I push that button, the clock is working. Now that's not exactly how I want it. I don't want to push a button all the time. So what I do is I add a JK flip-flop, which is that one here. I delete that line, put the output back to the input here, and now a JK flip-flop, if both inputs J and K are tied to high level. I'm doing that by connecting it to a power pin. Acts like a 1-button toggle switch, so I can switch that on. You see the state, light green is high, dark green is low, and I can set my clock on or off by simply pushing this button once or twice. Now what I also want is an LED that tells me the state of this stop button, like so. If I stop it, the LED lights up, my clock has stopped, and I'm just label that stop. Okay, and I will also label the button run stop button. Okay, that's the first function with a button. Then I want to set the 10 seconds, the 1 minute and the 1 hours with 3 more buttons. So I need to inject some signal here in this input of the next counter. So I can do that with an OR gate, because the next counter here should count when it gets a signal from the first counter or from my button input. Okay, that's the one here. Let's connect that. That doesn't look nice. Okay, so I move that down a little bit. I always like it when my schematics look a little bit nice. Okay, so, and then we need another button. I take that here so that all buttons are in one row, and I connect it here, and I call that button 1 second, no, 10 second. Okay, that's correct. Okay, let's test it. If I push that button, the 10 seconds advance, and of course the minutes here will advance too. So when I set my clock, I have to set up the seconds first, then the minutes, then the hours, and that's it. Now there is a little problem. Let's run that clock, because if the 9-bit here is high, that high level is passed through this OR gate to the input of the next counter, and when I push the button, nothing happens. So that means here with the seconds is not a big problem, but for example I cannot set the clock to something 9, because if that bit here is on, it doesn't work because it's already high. I cannot change it by pushing the button. So that means we need another gate here. Let's think about it. There must be a 1 if there is a 1, or there is a 1 but not both together. And that's a good thing here. We have a gate that does exactly this. It's called an XOR gate. That's an exclusive OR gate. Let's turn it around. And that means it does exactly what we need. Let's just... okay, I have to delete that line. Okay, let's do it again. It's a bit difficult here with overlapping lines and symbols. XOR gate, facing that way, because it connects right at the spot. Okay, now we have 5 inputs, we only need 2 inputs. Okay, that's it. So the XOR does exactly what we need. It makes a 1 on the output if one or the other input is high, but not if both are high. So let's see what happens. One input is high. I click on my button here, and you see the output line goes low when both inputs are high, and it changes. And of course it will also change when any other number is displayed on the 1 second. Okay, we need the same circuit here and here. Let's label that 1 hour. Place that correctly. So now that's the entire clock. Let's see if it really works. Minutes 34. 1, 2, 3, 1, 2, 3, 4. 34, okay. So let's make 35, because then I can wait until the actual time has catched up, and 11, that's already correct. So it's 35 and 21 seconds, and that's exactly now. So I have set it exactly to the second. Clock is running. You can see it's 32 seconds, or you just count the LEDs. Of course, in my clock we don't need LEDs. I have these rotary displays, but they are connecting directly to the decoder, so that's more or less what we need.